So hello everyone. I'm Tang again, the TA for this course. So today we're going to do a really brief crash course of eBPF, which is something it's the main focus of this course. Just think of eBPF as a powerful tool, but there are a lot of really complication in it that's we had to give you a tutorial on this. And a lot of the things are really not that well documented. So just don't be afraid to ask when you have any kind of trouble. We're going to hand out the homework in I think within this week, and it's gonna be due like 3 weeks from the day it's gonna be released. So you have plenty of time to complete it. But yeah, let's get started. So I want to give this first page, of course, it's an overview and objective. So eBPF or extended Berkeley filters, the focus of this course. Traditional BPF, which is used for actually like packet filtering, like network packet filtering, are going to be discussed I think next week or the week after next week. But we are actually going to see the original paper of it. But the modern eBPF, that's what extended is for, like the E in extended, extended in the E in the as for extended. It has evolved so much more than the traditional BPF that it have use cases that it encompasses from like networking, observability, security, and many more, even like scheduling, or it's just a really powerful tool that's an alternative for the traditional method to extend the operating system, which is for Linux is using Linux modules. So throughout this lecture, we're going to talk about what it is fundamentally or structurally, how how does it run? We just started, it's fine. How do we run it, and how do we get data out of the eBPF pipeline? So, and we're also going to be doing 4 demos to see its use cases. All right. So this is a really simplified structure of eBPF. So imagine that you have just think of it as a regular program. We call it eBPF program, but it can be written in a lot of languages. It can be written in C. It can be written in Go. There are Go binding libraries also available. You can even use some BCC library to write it in Python. And it goes through this compilation phase to translate the human readable eBPF program to eBPF bytecode. So the bytecode is kind of like assembly, but it's like it is represented in bytes. And you can use the LLVM tool to easily convert it to LLVM like intermediate representation, which is assembly like, but it doesn't run on any machine. Since it's just it's a conceptual ideas of the instruction. And if those 2 phases all happens in the user space, and once it's loaded into the kernel, it goes through this. The first we want to verify. We will need to verify the code. So we will sort of build an abstract syntax tree if you have learned PLT, and sort of traverse the tree to make sure it doesn't have like infinite loop. It doesn't have like dereferencing null pointer, all sort of things like that. So we're gonna see more detailed example after this. And then the next phase is it was quote unquote optional, the JIT phase, like just in time compilation phase. But it's adapted by most distribution of Linux. So what is just in time compilation mean? We're gonna see more in detail, but it basically means convert the BPF bytecode to machine code so that it's optimized and it can be actually run on the on the Linux on your bare metal machine. So then we can run it, and we have successfully run an eBPF program that extends the kernel somehow. So this is the overall structure of eBPF. We're going to see code example. We're going to see all the intermediate results, and we're going to draw connections. You also using this graph. Okay. So let's try to focus on this eBPF sandbox first, because we want to understand the architecture of how, like, what environment this eBPF program is actually executed in. So the eBPF sandbox is a RISC virtual machine. So you can think of it as a virtual machine. So it basically keeps all the states. It has registers, and it also has stack memory. And it can be executed on a conceptual CPU, but not actually like a CPU. So it's not actually executed. Please.
Oh, even on like an x86 machine, the eBPF sandbox is a RISC virtual machine. Like even if the architect like
That's I'm sorry, what's
Understand it. So when you think the two terms here of virtual machines, right? The first one is basically emulating. Looks like an x86 virtual machine, right? Like I use like a virtual box or VMware. There's another term for virtual machines, which basically means the runtime environment and you're executing. So the prime example that you understand is Java. Okay. So Java bytecode runs in a virtual machine. Python bytecode runs in a virtual machine. What does it effectively mean? It runs in a process. It's essentially every instruction that is this bytecode, right? It's a very high level bytecode, right? Or instruction set is going to be interpreted. Right? I mean, it's literally the history of Java over again.
I guess that's what's called.
And it's so damn slow, so people say, how can we make it faster? Well, rather than interpreting the instruction and creating the code, creating it. It would be useful. Why do I have to sandbox it? So everybody can ask questions.
Yes. Although we're gonna discuss it later. Okay, so I guess this terminology is sort of.
You can punt until later.
Yeah. I think the virtual machine, it's more closer to the Java virtual machine, less of like a virtual box thing. So it's a language runtime. You can sort of think, not language, it's a runtime environment. You can think of it that way. And it have this many registers. And we also have a stack, which is, let me move this. So it actually only have 512 bytes. So it's not too big. So imagine yourself, like, if you're writing the code in a stupid way, you're gonna max out the stat. So, also, okay, and that's the last register is the frame pointer, which points to the base of the stack.
So similar to what a Linux kernel does, where the stack is also limited to 8K or so. Right?
Yes.
There are a few no-nos, right? You don't do recursive code. I presume recursive code will actually be called by.
Yes, recursive code is going to be captured by the verifier to not let it run. So you can do recursion in the eBPF. That's one aspect of its limitation. Right. Any more comments?
But as it comes to recursion, most people should know you can typically do a recursion into a left loop or right loop kind of construct. Everything else is nested and that's not going to work.
Yes. Okay, cool. Then I can throw a question here. Where to store larger data structures? Any ideas? If you were to design eBPF, what are you thinking about?
Is this where the map thing?
Yes, that's exactly right. You use the map, which is, I would like to think of it as like a in-memory sort of like key value storage engine, which allow you to use larger chunk of, it's like using a heap, right? It's like using a large chunk of memory. So that's exactly right. That's what map is for. Okay. That's really quick. Okay. So
Oh, sorry, I have one more question with that. What's the reason for using the map instead of like, I guess a bigger stack or something like?
Bigger stack.
Or yeah, I guess why is there this whole concept of the map? Why not just give you kind of memory in the more memory in the first?
And I think there are also other data structures, like ring buffer, sort of. It's just maps are more common in the context of it's a traditional use case, right? For example, you have, if you're keeping track of some firewall rule, you want to sort of have a map, like the key being, let's say, the port number, the value being the like some flats, right? So I think it's more because of the use case, if that's yeah, we're gonna give the map. It's gonna explain a little bit later, but just I think for now we can think of it as some sort of heap memory. That's
Well, the heap in general can have fragmentation up to 50%, so that's a huge memory. The stack you can't arbitrarily increase, right? Because again, then everybody pays this price. But let's hypothetically assume you increase it to 4K, 8K, or something like this. It's still not enough to store many of the rapidly firing rules that are coming to this.
yeah, I think it's just somehow more constrained of what the data structure you can use for a larger piece of memory. Maybe, yeah, that all of them are really good questions. Okay. So this is a little bit more detail and a little bit more details on this what's actually there. So it's not too important, I guess. Like you're not gonna actually operate on the BPF bytecode or the register level, but it's just sort of good to know that R1 is reserved for returning values. R10 is read-only pointer to the stack base. And this is what we call like this is the format of the BPF bytecode. So we have the opcode. So this is little here. Anyway, this is the operation code, the destination source, right? Have the offset, have patterns. So it's basically just a definition of what's a BPF bytecode. So we're going to be seeing the in future slices. So how I think now you have a basic understanding of what's eBPF. It's basically there, and maybe it's now the question is how is how is eBPF considered secure? It's a secure environment for extending the Linux. Like this is mostly I think my generalization. So from my perspective, secure just literally means it doesn't crash and bring down the kernel, whatever happens. That's my definition for secure, but there could be more definitions. And to guarantee that, the eBPF does, I think, two important things to make sure of that. So it does verification and isolation. Oh, I'm sorry, this is supposed to be for verification. So we're gonna first briefly talk about verification. So verification is basically running through the code, generate the abstract syntax tree, and detect potential caveats in the code. So there is a doc for the verifier, but I would like to do a demo first to try to let you see a really simple example of the bounded and on the loop as we keep talking about. And then I'm gonna go refer to another guy's slice. He has a really good reference to.
I do not care that the time is bounded.
Oh wait, I mean it's okay that it's not bounded because eBPF also have a mechanism that's like a timeout mechanism. It only allowed you to execute up to this many, like several hundred Ks instructions. I think it's but it's just generally more
You think about where you're coming from, right? You're talking about hook points data, right? Maybe I asked that question at that point.
okay. Whew. No pressure. So this is my homework. Okay, let's go into the first example. It's a lot of examples we're going to see today. So let's go to eBPF tutorials. Let's go to number 0. 0 is a verifier, and we're going to make it. Already made. So I jump ahead a little bit about what actually a eBPF program look like. Like, don't care about this for now. Just look at this simple. This like the most forget about trace point, forget about what's CTX right now. Just look, let's make it a little bit bigger. Just look at the simple code. This is a bounded loop. So this is a for loop. It should let you execute. It should let you compile. And let's try to run it. Let's say verify. Wait. So we do. Oh, by the way, you also need root access to the. Okay, so you see it's attaching. It's not complaining. But what if I change it to like a while loop, right? That's one of the ways to generate infinite loops. Can immediately tell actually.
Condition while one.
That's true. So it fails. It said, what does it say? Let's look at the error message. Wait. Let's look at the error message. What does it say? So it's pretty convenient actually. You can see the dumps of the, you can see the dumps of all the, this is not even the byte. This is an intermediate code representation. You can see how this is subtracting, doing some offset. Basically, you can see what happened is that the type unknown size cannot be determined, which is basically just saying that this loop is unbounded and we cannot detect how many cycles it's going to run. And this is one simple example. Actually, I was running into some like weird edge cases, like it cannot detect. So I'm using an older version of the kernel. That's probably why, because when I'm doing like for, let's say int I equals to 0, let's say I is greater or less greater or equal to 0 and I plus plus, which is also infinite, it doesn't quite detect. So oh wait, okay, it also fails. All right, so I guess that's good.
What happens if the verifier is not intelligent enough to realize that the for loop actually will come here after?
Yeah, it works. I think I may have.
Well, actually,
Did I do this? Probably. Because this is
that's
that's literally just exiting. Okay. Sorry, that's a mistake that I made.
If you were to put like, actually, I'm just thinking, are there really no ways to like trick it? Is it like?
Of course, there are several like tons of exploration. It's a big thing in the security community, like finding eBPF bugs, right? It's especially in the verifier. And there are some like solutions to it. They're like formal verification for verifier. A lot of things, topics like that. But I guess I think it's good because it opens door for like security researcher to find new things to do, sort of. But yeah, I would say it's definitely more secure somehow than the traditional like Linux module kind of approach, but it does have some security flaws.
what they're effectively doing is they're doing kind of the evaluation of the terms, right? So if some of you actually, have you ever seen this blue curly bracket printf, curly bracket y0? The content is the while loop that, okay, you go through it once. It's the language construct, so you can do actually macro expansion and things like that. It's a very interesting trick. But the compiler will basically recognize it, don't only a while loop. Right? Or if you have code, and you say H0, right, in the simplest way, you can't then do something instead code, right? The compiler will not even generate code for that. It's now that's the simplest way, right? Sometimes you can actually do the math because there's a formula sitting there and the compiler will do this. And the verifier does very similar things. They're trying to reason over the syntax tree, right, of that little program that was written. Can I verify that this is a unbounded or bounded loop by either directly looking at it, right, or by effectively computing or trying to figure out what the computation is.
Yeah. And also just to bring it up, if you're interested in like PL or verification, I have a project idea about like using like model checking for verifier, and we can talk about that if you're interested. So this is so I want to probably go a little deeper in the verifier. I thought like there are better people with like better authors for this kind of content. So this guy, I'm not gonna pronounce his name, but he did a good presentation. If you just search on YouTube, there's a huge thing called eBPF Summit. It's like a developers summit, and like people give talks, like 5 to 15 minutes talk is pretty good. Like it's a pretty good way to, I would say, to find interesting topics to work on and see what other people are working on the eBPF topic. So he did a little bit deep in deep, and this is much more prettier. So he did a little more deep into the eBPF verifier. So he claims that it's all about types and values. So it's like some examples are like, let's just see some other examples, like return 0 as okay, but like because it's of type int. And return like a socket buffer, you don't have to understand what that is, but like if you return as like a pointer, it's gonna complain, right? It's pretty obvious. And compilers sort of like have better trust in user because it all it does is compile the code, but the verifier is actually more strict with the rules. So if you're like convert it to long, you're also gonna fail. If you wanna this is just some other examples of why it's not working. It's some macro stuff. I don't probably not going to use it too often. So it's also, this is about out of bound arrays. So it looks okay, but it's actually not okay because the I is externally initialized. So the verifier cannot verify the code within this region to make sure it's not going out of bound.
But let's go a little bit deeper into this particular code here. Right?
Mhm.
So when you remember what I said last time, right? The virtual machine, or the sandbox, actually lives in the address space of the kernel. That means if I can point to anything, I can get to the data. There's two problems. A, I can, for instance, point at somebody else's data structure and read it. Worse off it, I can modify it. Okay. And now because array is bound by 4 and I is not bound, ultimately this array probably lives somewhere in an address space or in a particular segment of your address space, and you're just simply overrunning and grabbing things. At that point, skilled people can, for instance, figure out what are the layouts of your kernel symbols are, which variables follows which one. So if I already know what your array is, analyze side channel, figure out what other variables has an offset to it, I can now basically compute the offset of the array that I would like to read. Okay? So that's basically why the verifier absolutely has to contain that any memory references that are being done are within this program. That's it. Or you go to more architecture that is like the maps.
Yes.
One more question about the verification thing. So does it also check, like you go back to the previous example where it's trying to prevent you from leaking that?
This one or
that, yeah. Does it also check like control? Like what if you say if this thing is equal to something, return true, else return false? Would it be able to check that? Because doesn't that like, it's kind of like a
So
control.
you typically you can't in languages like C, you can't check on the type, right? Type is always in.
Well, but I mean, if you check the value, like if this equals, 5, return true, otherwise return false.
It should be able to do that.
But doesn't that leak some information about what this is? Like, could you use that to construct? Like, that gives you some information about what this thing is that you're passing out.
Interesting.
I feel like can it do kind of that other, like another layer of
So you do a programmatic investigation of the data space.
So like
remember, you have access to whatever data you have in there. I mean, it's written that way. So you already know that the data. That's not your problem. The problem is when you go out of your range.
Oh, so the problem here is type, it's not leaking data.
it's about like different bytes, like sites.
Can you go back to the example where you changed it to like a one then?
Mhm.
I'm wondering like, what is it, like casting, how does, like, is this where instead of the function for that would return a long type, and we started with, let's say, an integer but casted it to a long, is that acceptable in the compiler and verifier and the other?
Yes.
And then my second question is with the, back to the array one, is there also, let's say I is bounded, right? And where, it's still externally initialized, can you also make the same argument for the character array? As in be that it's externally initialized and that it can't be returned.
Well, we define it here to be size 4, right?
Mhm.
So now, if the verifier can somehow figure out that I is between 0 and 4, like in that range, right, what 3 is, then it will pass, right? So it would be a really interesting example, you know, when you start playing with it, to just basically before the return, put an argument saying I is equal to 2. With the verifier, right? Because
Yeah,
that's a very simple thing. The typically value propagation happens, right? So
yeah.
sophisticated compilers will figure out that
Interesting.
values change, right? To try to keep constant as much as possible. I mean, if you look, for instance, if you said I is equal to 4, right? But I is equal to 3, that's a constant. Unlike
Mhm, yeah.
4, right? And a good compiler will treat it as a constant.
Yes. Like for me, I don't like me personally, I don't have much experience on verifier. Like all I'm hoping is that my code actually passes a verifier. Like if it doesn't pass, I was just like, damn, why does this not pass? So I think for most,
It's a source of frustration for us.
yes, it's pretty frustrating.
Put
That's
yourself into these constraints of having finite number of instructions that you can run.
and you're probably gonna run it into your
So you have to
homework.
break up the program into smaller pieces, right?
Mhm. So yeah, I'm gonna share the slides, but most of the things just gonna talk about how like compiler and verifier are different and that's how they do reasoning. It's that's how verify reasons. Like it could be out of bound, right? That's basically all it's about. So I think we should probably move on because I have a lot of things to cover. But I'm gonna share the slides. You can also check out the YouTube video, which definitely explains it better than me. So okay, let's go back. Okay. Isolation. What are we isolating actually? So those are the like list of reasons I can think of. So first of all, sandboxing. So it's a virtual environment, so it's the execution, it's isolated. Memory safety. We cannot access arbitrary memory locations of the code. Control access. Our view of the kernel internals are also limited. We can see the context, but for example, we cannot see like how test struct is defined in the kernel. That's really dangerous, and we don't want a user to be able to have that information. Also, this instruction set, as we define, it's a really limited instruction set. So you cannot do a lot of like crazy things. So what are one examples actually? What are some instruction that are there but not in the BPF instruction set? Like function calls, nested function
Calls are there.
calls, of course are there.
I mean, any kind of simplistic instruction set, load from memory.
Yeah,
load from memory,
yeah.
Right.
Yeah.
And then basically.
Yeah, I should think about this. I'm gonna come back to this because this is what I Googled online, is what documents say, but not I actually haven't investigated this. But
Like, who, I guess, decides what's safe and what's not?
it's controlled by the BPF program. So if you want to define your own BPF program, you're gonna see how you expose context to the user. And we're gonna briefly cover that, but it's pretty hard. It's really hard to like define yourself like a BPF type, BPF program. That's a lot of Linux code change.
I think you mean the question is different there. Because you said limited access to kernel internals. Let's suppose somebody who was scheduling trace point, right? And you're being handled the task point. Task point has a gazillion of things in it, right? Memory maps, you name it.
Is it pointer to the test struct?
Yeah, right? So most likely what you're interested in is that process ID, maybe the execution that is currently running, maybe the priority that's running, maybe what your parent is, right? But you're not into the data structures that can ultimately modify
Yeah.
significantly the state, such as the memory map, the applications in play. And so once I have the data structure, gave you the pointer, right? Well, can I do type conversions on it? Because I can look at the current Linux kernel code online. Yeah, like, okay, where's the memory offset, right? Very simple, it's macro right here. It tells me it offset 996. Oh, I do a cast on it. And voila, I have the pointer. And then we start doing this. I get to some other. And so what's the mechanism that prohibits me to look at all of these internal data structures?
So, for example, I think, do you mean like BPF helpers, which you can, BPF helpers is how you interact with the kernel and how you get data from the, how you get data from the kernel. For example, the PID, for example, if you're doing scheduling. There's also an alternative called kfuncs, which is like developed specifically for schematics. It's very involved. So just like I'm gonna cover BPF helpers, which is essentially a way to interact with the kernel and get data get information from the kernel. Not it's like it's crazy for.
So every kernel object's being passed to you is effectively opaque, right? I don't know what the internals are, right? I can look it up somewhere else, but I can't get to it. And that's what the other functions do for you.
Yes.
They're very limited.
Yes, we're gonna see some. I actually one of the biggest challenges to like when I'm doing the introduction, which slides I'm gonna put first, because it's all like a little intertwined. But hopefully you will get a good picture after, like after you have a basic understanding. So some questions. Yay. So what do you think actually? I guess, oh wait, you can't see it. Okay, it says, can BPF call arbitrary kernel functions? It sounds like no, right? It can't. It can only call specific functions, like BPF helpers, as we're going to discuss. And also, like for each program, there's also only a limited set of functions that's defined. And we're going to see the man page of it. So don't worry, we'll get there. So can BPF overwrite arbitrary kernel memories? Sounds so stupid. No. So somehow you can read it with this helpers, but also maybe you can, because networking programs cannot do that for some reasons. But I'm actually not sure why. So Hubertus, do you have an idea on why a networking program cannot read it? Maybe you will have to read the design docs. There are like the design docs on Linux, because
So the reason for that, sometimes in the BPF program, if you want to look at, let's say, content of the packet, right?
Oh, right, snooping the packet, right?
Right, so they're usually somewhere on the or somewhere. Want to potentially do a content analysis, like that to effectively get access to those. But as you can see from the probe read and probe read string and so on, they're very limited. Right?
Yeah.
The difference to verify that you basically within the offset of the data file.
Yes. So can BPF overwrite arbitrary user memory? Yes or no? Just its own process.
No.
Sort of. Okay. It has some right users to it, right? So it can somehow, but it will generate warnings because it's contain its user memory. So what's the worst thing you can do? It's just like crashing your user process, not like crashing the kernel. So it's somehow okay, but it's just not really commonly used. But you sort of have an idea of like how it's preventing, how like if you want to do kernel memory like manipulation, right? You can do it.
One example would be basically bypass the kernel interface. Typically, data needs to pass through that kernel interface, right? send out data to the user space, you're better doing them with a bin buffer or something.
Mhm.
Right? But you technically could just inject it into somewhere in the memory.
Yeah.
Not advisable. But
Mm-hmm.
But that is, so you could in the,
let's suppose you're trying to write a memory, the user, and then memory is paged out. Or you get a page fault.
you have to make sure you handle that.
Well, you might be in a BPF function that can't handle it.
I'm sorry, what is?
You might be in a BPF function that can't handle faults at this point.
Yeah, yeah. Mhm.
So that's when it gets very tricky. Question.
Yes. So BPF programs, like you may have imagined, cannot go to sleep. Oh, it can, but most usually you can't. It's a sleepable BPF. It's much of a beast. So you can imagine, like, you cannot do page fault. You cannot handle page faults in BPF programs.
So, sorry, this is like kind of going back to the basic stuff. Is it running, so it's running in the context of a particular, there's like a user process that like when it says its own user process, I guess, is that the process that like loaded it in, or? is that the
Yeah,
process-
it's literally the next slide. So there you go. It's so what happens is, for example, some kernel code is running, and then you encounter a BPF hook. That's how what it's the same process, but it's just when you encounter a BPF hook and you have loaded a eBPF, you're gonna go into this eBPF sort of sandbox environment, which does a set of instruction, have access to a certain limited resource. Then when it's done, then kernel code resume, right? So does it answer your question, sort of?
I think so. This is for any, so like, I'm some user space process. I add one of these eBPF
Mhm.
functions. Then some other context or some other process is running. It hits the hook location, and then that function will still run, correct?
It hits the what
Like,
location?
so I have one process that loads the eBPF function.
So that's
Then
one.
I switch into a new process that's running something completely unrelated.
Yes.
It calls a system call, it goes into the kernel, and hits my eBPF function,
Mm-hmm.
and then it will run that function.
I don't think so, because I think it's PID specific.
Okay.
Yeah. I am not sure about the mechanism actually, because the hooks, it's really weirdly defined, I think, in Linux. It's if you actually look at one, you can there's like a book like this thick of like how like explains it, like by it's amazing Brendan Gregg explaining that. But it's basically I don't have a very good idea of how hooks are implemented, but it should be PID specific. So it's
It
just
depends also, right? You might, let's say if you go into networking, that's lower in the stack, right? Some network functions are effectively not running in user context, right? Because they're on the receive side, right? As they're pushing through the TCP/IP stack, right? Most likely, well, pretty sure they're not process specific. But if you're coming from the top, read hooks, they're fully process specific.
yeah.
The documentation.
So yeah, networking should be not process specific, but it should be in the documentation. I don't know how it's implemented, but I think if you look into it, you could find some answers. So hooks, so there are like tons of different kinds of hooks. So, trace points, k-props, u-props, perf events, blah 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 blah. Security hooks, networking hooks. So all these kind of hooks have different, very different definition rules, and there's different things I need to care about. So it's hard to go into detail to each, but I would say if you can choose one to like focus for your project, sort of. But we're going to run examples on them. So right now.
To give you an idea, I think I put it somewhere in the slides here. Under 20,000 full points in the kernel.
I didn't know the number. That's a lot, yes. I think most of them are like k-props, right? Yes. K-props is like just like when you are hitting like a kernel function, you can sort of like invoke that eBPF programs with k-prop and k-return prop. Like when when it enter the program, when it returns, sort of. But I'm not a master of K-prop. It's literally hard to be a master of eBPF because you can sort of see that if you want to master eBPF, you have to be a master of everything. You have to be a master of architecture, PL, OS, networking. It's everything. So it's a lot of Googling around, I'd say. But it's fun, right? So we're finally going to hit some examples and not going to be as abstract as the previous slides. So just a little disclaimer here. It's gonna be a little intimidating because the examples are in the most difficult tool to be used. Sorry, that's blocking this. So a lot of great tools are written by a lot of amazing programmer, but we're going to use the most difficult but yet flexible binding, which is the libPF. There are also other tools available. BCC, it's in Python, but you basically it's also like you need to learn a little bit about like how to define a program, but it's in Python, so you can imagine it being a little easier. BPF trace, it's also built on top of libBPFs. So BPF trace, it's yet another thing, but it's mostly for tracing. You can see the flexibility sort of like decreases here, so it's more for a tracing project. And it's actually a programming language, so you had to learn the grammar a little bit, but it's really easy, trust me. And you can use it for some really cool observability, really easy to use command line tool. Oh, the Cilium. The Cilium is for Kubernetes. I'm not sure how I haven't used it myself, but I heard it's pretty widely adopted in the industry. So I think it's worth mentioning if you're interested in like serverless cloud computing sort of stuff. So just like you can choose whatever tool you use, but just be aware of like what the flexibility and complexity you intrinsically have. Cool. So, all right. So this is I put this graph here because I want to illustrate how we have already seen this part of the program, right? We have already seen it's being compiled, being loaded, interact with the maps. Like how does the user interact with it? So that's where we're going to talk about. That's what we're going to talk about. It says here. It's with the C++ libBPF library, which is also available in Ghost. And what it does, interact with the map. It handles all the. It's just like a layer for you to write BPF code as a user. Instead of you directly calling the BPF system call. So basically everything you want to do can be done with BPF system call. So there's a system call. Actually, let us see the BPF system call. Why don't we see the BPF system call? You can see why.
321.
Oh, okay, let's yeah. All right, let's see what's how do you remember the number? Let's see the man page of it. Okay, this is all. Like this is literally all. But how do we use it? Blah 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 blah. Forget about it. Let's just see the examples and the example use case. You see? Defining all these sort of like assemblies by yourself. Do you really want to do that? Say probably not. So that's why we use a layer. It's called the libBPF. That's here to allow you to use slightly easier abstraction. Got it?
That's like user space code that you can then use to like load the eBPF program.
This is system call. You can do everything with it. You can interact with the map. You can load, verify. You can see this.
Think of it like everybody knows what an IOCTL is.
IOCTL.
Yeah, so IOCTL is basically like an IOCTL. The difference is that there's no device behind it, right? But you can pass anything to what you like to this IOCTL as long as the other end knows what it is, right? So BPF basically define all these commands that it will basically do. Can you show me the eBPF code again. Just all the way at the top. All the way at the top.
Oh, okay.
So you see that the command,
Mhm.
there are basically a finite set of commands. And then you just basically passing in the arguments to the traffic keys, right? Which is basically a data structure that is targeted for the commands, right? And it's basically a switch. Like you click it in and then you come with the default to command what you actually want to do. Now this is somewhat nasty, so people basically provided macros around it, like BPF load program, what does it effectively do with
Yeah.
BPF and command load program.
Yes.
Okay.
That's well, but I guess the libBPF. Let's actually see the slides first. This breaks it down a little better.
You get to speed up a little.
Oh yeah. So I'm sorry. That's I have. Oh, I'm at 13 now. Okay. Had to be really fast right now. Go. Okay, so that's this is hello world. So hello world, we're just gonna trace how we enter. We're gonna trace every entering of the system call, and we will see the full list of your machine of where are all the trace points here under this like sysfs. So let's illustrate both. Let's illustrate how to find the trace point and also how to find the okay, let's actually first look at the breakdown code a little bit. So this is like first is some boilerplate templates for the eBPF. You have to have a license somehow. This is the actual BPF function. And this program, like say this is like get the current PID of get the current PID of the process which interacts with the kernel. So we do it with the BPF helper. So helpers are for interaction with BPF. And this is also some helper function to help you to print, to help you to put in a buffer because it's not going to go to sleep, right? Remember what I said, it's not going to do this expensive kind of blocking thing. So it's after the exit, it will like print the buffer. This is what we call, okay, how do I break this down? So this is the BPF program. It's usually like with the suffix like BPF.c, for example, like XXF BPF.c. So you can see this is C format, but it's actually a BPF code. But you can use Clang to compile that with targeting the BPF bytecode, right? It's like compiling and generate the object. And then we can also see this object since it's, trust me, you can run it yourself. It's a lot of hassle. I don't want to do the live demo, so I already printed for you. So the .o have all the information you're gonna need. You have disassembly. You can see the assembly. You can see the bytecode here. So notice that this is the BPF bytecode. So it's not machine code. It haven't gone through the machine like the JIT compilation phase. So it's not native machine code.
Can we assume that 14 is actually the handler for BPF get current bit? So every function.
I think so. Yeah, I think it's it's the first thing that's get called. Yeah. Also, like BPF have really weird padding rules, so you can it's some you have to like move it by a little bit. So do expect a little bit of that in the meantime of development.
Most likely in this particular function, you're returning two things: the bit and the task of the thread body. Okay, that's a 64-byte number. You mentioned earlier that all the registers are 64-bit.
Yes.
No one function out of the BPF ever functions extended to some degree, right? And so they're returning actually more data and then
two at a time.
Extract it out.
Yes.
Yeah.
So you literally have to do your bitwise operation yourself, or like to get this higher PID. The thread group ID. Like this is PID, like this is PID. You can also see the symbol table. You can see it for yourself, like symbol tables, the like sections if you're interested. It's not too important, I think. And so this is not the BPF code. This is how we use libbpf to load, to like not load, verify, load, and attach the BPF programs that we have already compiled. So you can have tons of like logic here. You can see an example of like, we will have an example of drawing a histogram. I think most likely for the homework, you're gonna be drawing some histogram in this thing. So the main problem that this main thing can be really like, for example, complicated. They like do keep the BPF program simple and only put really key ideas there. So let's just go through it. This is more convenient. So you will open the file, which is the compiled object of the BPF program. You will attach it, right? You will find the program that you have loaded. And you will see all the sections. Remember, we have different functions, like we have different attach points to the BPF program. So we find this a particular handler for this trace point. And then this program ID is to get the file descriptor of the program so that you can attach it to the trace point for this specific program. And then I think do we have questions? I think it's worth pausing a little bit. You can all see the struct definitions when you search online. It's really complicated. I think it's better to just see the examples, right? Okay, so let's actually talk about that before we actually go to the example. So this, what is this? This is ARM code, right? You can see that it's clearly ARM code. It's not the BPF IPO anymore. So this has been JIT compiled. So this is the JIT compiled ARM assembly code, which are all things that you probably have seen. So this is, and you can also see, let's see, right, the register, there are definitely more than 10 registers, right? So that's another way of seeing that this is the machine code, not the BPF code. And then let's just run it actually. So we go back to the example. Let's go back to the hello world. Do you need a break actually, or do you have time? Let's make it okay. Let's oh wait. One example. Let's see. Let's trace pipe. Let's see. Trace pipe. Sys-kernel debug tracing. Sudo cat sys debug kernel debug trace point. Thank you. Trace point and tracing and trace pipe. Okay. So trace pipe is the output for the printk function. Wait, this already loaded. I'm loaded. So when I sudo execute the hello world, that was like that. Those are like probably from like previous run, so it's not buffered.
Times that 56, 57, and
What's happening? Hello world. Okay, so this is, as you can see the logic, you can see a lot of like see which system calls are invocated, because we remember the attach point is sys enter. So you can, this printk prints to this pipe here, and you can see all the system calls being invocated. Probably a lot of cat because we're opening a file, probably a lot of SSH, right? Pretty expected, right? So this is the most simple use case of the hello world. Once again, I would strongly suggest that you run through the code. So you can see a lot of this. It's I think if you run it yourself, you'll get it what to expect here. sort of. It's really hard to explain with words. So that's one. BPF largely uses sysfs, which I think it's good or bad. We have seen this it's like transition from code to bytecode to assembly, which I keep emphasizing. And we have logged some events with Franke, right? It's all documented here. You can try running it yourself. Then let's try to see a map a little bit, actually. Because we say that like the stack is probably not too big to be useful, so that a lot of the useful program need really large state space. So BPF maps is how we maintain space and get the data in and out of the user space.
You put it in the slideshow.
So oh, sorry. Says how we interact with the user space, because we also have the BPF. For example, you're gonna see all the BPF how like get element, put element from the map. So it's a way of interacting with the user space as well. There are a lot of maps, hash arrays, right? There are also array maps, which are really not that commonly used. It's mostly used for hash map. There are also global and per CPU variant. There are also data structures, all kind of data structures that's being pushed out I think every week, every month. So it's a you have to see the latest document for that. So the basic idea is that there are two kinds of maps. First is global and second is per CPU. Do you guys have any idea like what's the potential difference of the two? Is that?
I have an idea, but
I'm curious, like, when you say first view, is this per like actual CPU or I guess
It's
like,
actually CPU.
thread on the.
It's actually CPU. So if the data structure, it's like if it's executing on CPU 1, it will interact with this map, right? If it's 2, it will interact with another map. Right? That's why would you want that? Well, Hubertus.
you did answer the question. What do you think is per?
Is that maybe for performance?
Yes, it is.
Well, think about it. Two CPUs that are completely uncoordinated in the kernel, writing to the same memory address with the same key value, but you never go on. You have a race condition.
Yes, they have a race condition. You had to have a lock. So that's the issue.
So first CPU one don't.
Yeah, but you have to aggregate later yourself.
Yeah.
So that's I think most commonly I usually use the per CPU just for the performance, but you can do both. Either way is fine. Shouldn't have. Now that I think of it, I shouldn't have put BPF helper this far into the tutorial, but as you can see, the BPF helpers, we see this get current PID TGIDs, how it interacts with the kernel function. So that's what helper does. So there are also kfuncs, which is using scatxt. It is out there because of scatxt. It's essentially, if you have taken OS1, it's like those callback function that you define, like it's pick next tags, sort of that's then you have a sort of like a function pointer defined. If you're interested in scat.exe, you can read into it. If not, just forget about it for now. So you can use it for get PID, also use it to interact with the maps, right? And then the BPF helpers are basically, I can think of it, it's an eBPF program to like BPF to helpers to BPF is system call to like user space program. If that making more sense to you. So other helpers also there. It's I think this is I think where I look at this is my preferred way of getting of using the Mac using like finding what are the helpers available. This is this is the most commonly used map, like it's interacting with the map for the BPF program. That's usually the most commonly used one. I don't know, we don't add perf event timer, you can see all the things, right? It's just look at it for yourself. Okay.
You have that, leak access?
Yeah, it's here. And also there's man page, but I guess it's less readable. But probably more up to date. So yeah, it's XDB, as we're gonna see the example. You can define your own helper, but it's hard. Okay, so just to do a little recap, it's just like I paste the code here. This is the program code. It's like reading in C syntax, but it's actually eBPF program. It's trying to compile to the bytecode and load it and JIT it to this machine code. That's the point I'm trying to get here. Because I got very confused when I was first learning it, so I just want to clarify that. So system count, this is an example for us to actually dive deep into the map, which is the most commonly used thing. So we're gonna have to see. We're gonna see. So in this task, we're gonna count how many system calls are used for each system call. So you can imagine the very easy cases that we have. So the key being the system call ID, and we want to count it over a period of time. For example, 1 second, 2 second, 5 second. So yeah, this is the code. The hash map is the most often used to use the BPF map. Like it's called map, but there are also other data structure, but you also call it map. I think it's somehow weird, but like, it's I think for historical reason, it's just the first thing that was out there was the hash map. So this here's the illustration. User space process read with the libBPF infrastructure, and then eBPF program interact also write with the BPF map with the BPF helpers. That's what I'm trying to get at here. This is how we define a map, hash map. So so you can see this hash map, the per CPU hash map, right? I see it here. It's all macros, so it's a little hard to read, but bear with it for a second. Key types, it's an integer, it's an unsigned integer, 64 bits, and value, it's types, how many entries it can be there. Yeah, it's pretty obvious. And the sections are mapped, just don't remember to, and it's call system call ID to count. It's just pretty obvious.
Okay,
Okay.
I think the same question.
Oh, why do we use?
Why such a weirdo syntax? Why not just basically write key is UN64?
I actually don't think that's
You
too.
ever run it to a minus E? You combine it with minus E, that should actually resolve all the macros.
I think it's just like a compiler guys trying to be lazy. I guess it's easier to parse or something. Since this is only like this is C library specific, I think Go uses different syntax. I think there might be some conflict of how to define it, but I think this is the choice that they made. I think
What happens if you overflow max entries? Does it?
that's a good question.
Throw sometimes.
I think it throw an exception, but I haven't tried to actually overflow it. So
That's 100%.
it can. It's like the kernel, like the Linux won't crash. The worst case scenario is that your process crash. So that's
It does crash if we take down the store. That fix it.
yes. So you can, that's another example of like how the eBPF community is fast, like really quickly iterating. The next version they put is probably going to be not compatible with the previous version, which is going to be solved by a new feature of the eBPF. We're just going to be covered just a second from now. Too many subs, I'm sorry. Do you need a break? I think it's a lot of stuff.
You need a break.
No, I think it's okay, but like
You finish example 2 and then.
okay, let's do example 2, and then briefly it's a lot of stuff. That's a helpers. As helpers, you can do lookup, you can do update, but the syntax is also a little weird. I agree. So but just try to read more of the menu and try to use it wisely. That's all I can say. Yeah. So And also you need to use a pointer, because, let's see, why is, because we are, actually, why? Oh, because it passes you the address instead of the actual value of it. Which should be,
There's so many interesting, you're really trying to get into this, right?
Yes.
Trying to figure out how this piece works, right? So
can be,
when I look at this code and I get the asterisk value, I would immediately increase the value by plus plus and put a bracket around. Because at the end, what you can see value is nothing else but a pointer I can see in an array. And I pointed anywhere in moments left, right? Let's proceed, right?
So, I guess I'm doing quick, you're allowed to dereference this, how does it know that value, I guess it's with returned by helper, it knows the value is okay, but you can't access, I guess you can't pass value to anything else.
So when it comes, here's my theory, I've done some compilers with you for years, right? So when the value comes back from MBB map lookup element, because it's a well-known function, the verifier will basically mark the address of value and now track whether that address is basically written or changed. Right? So far, it hasn't been changed, so when you write back to it, it knows it's a kosher address that was handed from the eBPF function. That's why one thing I would do is I basically increment value, the pointer increment, and then try to write to it. I guarantee you that, well, I mean, yeah, but I bet you nothing, of course, that the verifier will fail on that.
I'm actually interested in why does this code that I copied from the tutorial does +1 instead of another update, right? Or you can also do update technically, but that probably is more costly. So I think it's more efficient and it allows you to do this. So I guess we can do. Okay. The user space portion, which that's a BPF map, get next key, BPF map, look at element. It's just it's what libBPF allow you to do. It's all macros, very nasty. So let's get to the
Go back.
well, oh, actually do you want to see let's see it. Oh, okay. Yeah. It's easier to see somehow. It's because it's dark, right?
The other while loop somewhere.
Probably.
Presentation.
Really? Because this is a user space code.
So I want to go when I reset the map. So the map is basically, if it's not updated, it's effectively non-changed data structure. Right?
Mhm.
So first time I iterate through it, it's fine. So how do I know that that I'm starting out at the beginning? Is that basically done by setting the current key to null? First line, I set the current key to null.
I set the
and
current,
I
yes.
start iterating.
Yeah, start iterating to it, and I'm assuming if it's returning 0, like it's returning 0, then there's gonna be the next one, right?
Okay.
Yeah,
First line. Okay, cool.
yeah. So yeah, I don't know why that's there actually. I think it's probably okay. So this is I have to break this down a little bit because it's a little hard to understand. This is a while one loop, just does constantly getting record from the map and then clear it up from the user space. So you can see this is a sys count.c, it's not bpf.c. So you get so that's how it's how it's BPF program interacts with the user space program, this map.
Maybe it's this example I don't really well. I see my changes in there. Can you show the BPF program again, just to basically go through this, right? So here's the source count, right? It is basically called every time the system call is made. Okay? And so I get the syscall ID through the context, right? So that's usually described in the documentation. Basically, in line 36, I'm looking up the element, right? So that's the skull ID, right? And then I basically increment it. Use that out there. Okay. So if the value exists at that point, then I set the value +1. Otherwise, I basically initialize that value there to 0. That's all I do. Every time a system call is, I go to the map. At that system call number, I basically implement the thing, right? That's all it does forever. Now I basically go to the user level program, right? So the convention that is being used is that eBPF.c is the BPF program. If you don't have that, then you have the user program. So if you take a look at the system, what it does every 5 seconds, so right at line 450, right? What it effectively does, it goes through the map, right? So it iterates through the map in line 454, gets the next key, right? And basically looks up where that where the total is, right? You can see in line 52. It's basically adding up all the values across all the CPUs that we found.
Is it doing blocking internally, or is it just reading so it doesn't do it?
Internally.
Doesn't even look, because it's the CPU.
Well, I mean, for here, when you're aggregating them all together.
That's basically, that I don't know, you know, so that it's out. But you make a good point, because at that point, I'm doing a read, if somebody modifies anything at that time, that's what good.
Yeah.
So there must be probably, around these functions, BPF map functions that are somewhere.
Because it's user space, so it's not happening that frequently.
Mm-hmm. Yeah, so that's, yeah, that's, shall we see it?
Difference.
Mhm. Oh, wait, this is hello world. This is the two syscon. Make and then syscon. Oh, yeah, that's why you can see I forgot the pseudo, so that so it doesn't allow you.
So because of the explosion of the verifier and everything, there's very little trust based on actually following the premise of what BPF was, which basically, hey, that's the anybody can download stuff. So now they basically say only the super user can download. So you're running on an ARM, right?
No, this is x86.
Oh, okay, now I see the BPF is 321, yes. You can see every
Yeah,
5 second update.
you can see
That's
pool.
all in that particular period of time, right?
The big four is always at the top, sort of. Nah. 0, 1, 2, 3. But you can also sort it, right? So all the things you can do. Like this actually like it's open up the door for like potential cases, right? So I'm gonna give a reference to like where does this program come from? There is a like the BCC tool write a whole library for that because they wrapped it around the Python Python. I mean wrap it around with Python. So they all like all the implementation sort of come from there, which I'm also gonna get appointed. They have like tons of examples and you can look through it yourself. Cool. So that's a second example. Should we continue? We have 1 hour. We have okay.
Can you get 25 minutes?
Yeah, I think I can. It's XDP is pretty straightforward. So
Let's take a 5-minute break.
okay. Yay.
Thanks. Meantime, your question.
Actually, my first, like, I don't know, but I'm just shocked that it didn't cure at all. Like, I guess my like, and you're just another design kernel, right? They're doing it all down and send it, whatever design kernel is best for them. None of that was ever meant to be like previous, like an interface that could be saved to be exposed. I'm just surprised there's not a problem with like.
My best. That is true, right? Because particularly when you pull a chance, right? And you know, I heard that.
Oh, I took that, yes.
That's right.
Yeah,
Yeah, that's like.
How?
And so, so you very well know what a core channel is.
Yeah, definitely. It was like,
Collecting
those
data,
will work
taking out
because
some means,
we
right? Yeah.
chose it
eBPF is
public,
perfect for
but
that. I mean, if I can just basically see how often this gets scheduled, right?
Yeah.
I mean, there have been,
that
one of my favorite hacks that I've ever heard of was, when people, they know when your time expires, it's easy to figure out, you run your program forever, take the clock, because your user has access to the clock, in nanoseconds. And you just see when somebody else took over and then.
We only.
Yeah.
And so over time, they learn how quick, what their time scale was.
It's really
But
fun.
just before, they ran something, just before the time was up, they put their program in such a way.
Like, it somehow sucks up that like,
They did
it's
it.
like, sort of like, throw away some packets.
About microsleep or something.
That was like-
And microsleep typically sits in the application, it doesn't, it's not counted as runnable, right? And then when that microsleep was over, they continued. As a result, they published what they top. Why? Because top comes sampling. Every time the timer fires, like, who's running, who's running? Right?
Okay.
And they were completely
Because,
incognito, and
yeah.
I was sucking about 95% of the CPU cycle.
Oh, wow.
While the system showed, yeah.
One of our teammates.
That is good, yeah, right? And you can imagine a program like this.
I would
at
like,
least in particular now that the schedule.
Two of us, like, they're not.
And you wouldn't need to be at all, not even nearly. as
They're
big.
trying to figure out that. Hard to.
So, but I guess that's part of the reason
Starting
why
to
we
get them on board actually.
root access. I guess I think it's not like that as much about Linux, like security. Like, if you already have root access, I suppose you could like load a kernel modules.
One of the professors
So like
told
root access,
because
it's over at that point. So, I guess. Yeah.
last year through those projects.
So then I guess, but if you need that.
I
to-
think
to load-
I like that style.
Well, you use pseudo, right? So
Yeah.
it allows you to do something. I
Um,
mean, most of them have
because
started to get paid.
I like Cosmos.
I have to look this up, but, you know,
Also.
I waited as long as I know that the class was actually taking place, right? But, in general, the way you do that is with capabilities.
There is gonna be just.
So this is.
Helps you get on board.
I've actually not
So
interacted too much with
those.
Linux yet. I mean, I know they vaguely exist, but there's.
There's security.
Yeah.
So there's
Last slide.
And then-
Yeah,
in
the
security
budget
modules,
one slides.
right? So you see,
Paper reading deadline for discussions.
Yeah.
right at the beginning,
That's
somebody,
for like-
and NSA, who I worked for like 2-3 months.
That's a separate. It's like,
When we talked about, you know what SE Linux is?
that's gonna-
Heard the name.
So SE Linux is basically, there are two frameworks. Okay? One is called,
Do we have like any programs read last
there's SE Linux,
Yeah.
ARM,
It's gonna be most.
right? There are two frameworks. And then now you specify security
If you
policies.
wanna think for.
Underneath, you have what I call
Yeah,
LSM,
and that-
Linux
that's
security modules.
Usually.
These are basically
for
implemented
my
at 2
experience,
points. Like that.
If you have a good idea.
And so, you basically determine what
Catch up with
a particular user can do. You negotiate with the LSM model, am I allowed to do this?
Okay.
You can do that at file access,
And then it's just
right?
like a final.
You can do that execution. So for instance,
I would
containers
find
will
it
get certain
really
rights. Right? You can do certain things and they can't. do
It's
other
not bad to
things.
read.
That's all done for instance by limiting which system calls they do,
Okay, yeah, I think I remember
Not sure.
this.
right? There's something called SecCon, right?
I guess reading a paper
And,
doesn't.
Yeah.
you make a profile, you basically hook yourself to these system call things, right?
Down.
And say, okay, what is this one?
Quite a lot.
The fastest was effectively done by doing
It's,
secondary system call data,
2 papers per week.
not
It's a little
kilobyte.
heavy.
Yeah.
But I didn't survive.
And so you would make a
It's
like a
nothing.
system call data, a copy of the original one, and then
Yeah, yeah, so.
fill everything else that you're not allowed to do.
It's pretty fun. Yeah.
So, and that would be done under the kernel. Early, so to speak.
Yeah, so I guess that's not too different, like, what I'm more familiar
If
with. how we do it.
you participate in classes instead of. Not. And you.
But
do
yes,
this
I mean,
on
on
top
top
of your
of
project,
it's
not
just
like, you don't have to get any results, like.
I can see that becoming a much,
If you're
like,
trying-
unless you
It happens.
Unless
all
you
the time you research.
kind of
You try
convert
something,
all of the potential
Try
subwords
something.
and things that you can actually
So
instruction.
it felt figured.
Unless you kind of go through and like
Take a
apply
swing.
the ability to chop those and decide
And now.
the intelligent
Third
things, yeah.
So I
Like,
think
that's usually
hopefully it will
quite
work.
dangerous to
That's right.
That's,
Yeah.
it's
All
okay to
internal kernel functions are not
sort of
necessarily
not
security
worry
boundaries,
about
are now.
that you sort of
sources
did,
some kind of, like,
you did.
Now you have to
some
decide
following,
whether or not something
you
is
did some
based on
experiment. you sort of analyze.
So the nice thing about
here.
eBPF is that you can maintain state, right? So you can actually say, well, this process just an map and then the read versus the remap. Right, in policies along the line, I think this would be very interesting. But we really want to go down that ransomware thing and discuss it after a little bit research work. Just we find to read because at the end of the day, writing code is one thing, exercising is different. So couldn't really find everything when there's an open source ransomware.
He doesn't talk about
Tool for protection. But from our internal side,
That's some sort of like, all sort of like.
FS notify.
Cloud.
But in FS notify, you're now basically sitting
Like
in the user level application, you have
Right now.
application now.
Yes, one of them is.
So I'm wondering whether some of these things.
Cloud, Rust.
So FS notify, which gives you a handle,
It's
pretty efficient, right? What you do is you have an application. It's basically lock until an event comes in, like,
Hopefully, yeah.
send it out, right? That's all.
That's.
So you probably-
I'll have to-
I've like used it once or twice, but I.
It's the same thing, you can select. You basically get a
Do we have?
file descriptor or set of file descriptors, right?
Yeah,
And you wait on it, and if anyone
People is the new version of
So I
Select.
call it a new one, so that basically says, give me a set, of anything happens, you raise an event. Right? And the default basically will unlock, give you one event at the same time. Previously, it's the next, you have to give a file descriptor.
And then you.
They made a bitmap.
You get all.
And then you have to search the event bitmap for the one file descriptor that
I heard you guys
change.
also.
Yes.
Really good.
Yeah. I mean, we did a,
If you're doing.
for this other class of MTA, what we did, and assigned like a web server.
We're literally paying.
Okay,
that's what we're doing.
Now you have to speed up a little bit. I don't-
Yes, we will do that. And let's run the XDP example. But let's first talk about what is XDP. Oh, also, if you're really interested in observe. Okay, I guess we have 2 leftover slides. Briefly talk about that. Those are my sort of experience in finding where are the trace points. So you can run it for yourself and you will see all the kind of trace points all listed. Just try to run it. If you have problems, go to me and we can discuss about that, right? So just like list all the tracing, list all the perf events, try it for yourself. So it's all sysfs. If you're really interested in observability, this is this book is this thick and it will go through it in depth.
PDF version of that?
There is definitely. I think it's on his website if you Google. Yeah. Okay, so we're going to see how eBPF is originally used. So we were trying to get information from the kernel. Now we're actually going to try to handle something. For this, we'll go into an example for firewall rule defining XDP, which is express data path. It's how is it expressed is that it bypasses the entire Linux kernel for network processing. So you can imagine the use cases being first sort of like BPF program reject or forward a project without going through the Linux networking stack, which is notoriously bad. So that's his original use case. So you can imagine that you just go through this eBPF without traversing blah layers, networking and Linux. And there are also security, which I will provide some pointers, but I'm not a master of that. So if you want to do security, oh, that's those are the things you should be looking at. So networking. Let's see a XDP example. So the program type for XDP are BPF program type XDP. Once again, you can see all the kind of program type defined online. And basically what it has is that you have several actions. You can drop the packet. This is to say you receive a packet, right? You can drop the packet, you can pass the packet through the Linux SAS as usual, and you can try to redirect the packets to the same NIC or to another network interface card. So I think let's not waste time just like trying to. But this is a message, like this is a message buffer for the firewall routes at the Ethernet header, epi header. We're gonna use a UDP use case for that. And we will try to block all the UDP connections on 11111. That's what it does. So just look at the code. The reason why I talk about really briefly is that it's like this use case, like XDP, is more well documented online. So it's because it's how it's supposed to be used. So yeah, I think it's parse like because you bypass the Linux network stack, you have to parse the network packet yourself, and you're passed you get passed with this XDP context, and you will try to parse like what's the protocol, check the parse the IP, verify the protocol if it's actually UDP that we're trying to drop, like here, right? We just block UDP port 11111, and we're parsing UDP, blah blah blah. Verify checker to verify it so that it doesn't go out of the range. Then finally, we will block the 1111 port. So let's run through the example. This is a pretty and most interesting use case I've ever seen. Just to run it, I prepared two bash windows for that. So once this. So let's use this window to listen on the connections that's happening on the 1111. So that's, you can think of it as a server, but it's actually just set up a UDP connection. That's a listen for the connection of the UDP. Then we're gonna use this one to start a connection to establish a connection with the netcat command line. It's actually clear. It's a little.
Do you understand what the netcat does? Because it would be quite useful for you to.
Oh yeah, so I have a comment. I think it's
Send out the packet, right?
yeah, sends out the packet. It's this, like the left one's listening for the connection. The right one is establishing a connection. Now we can finally let's well, the 1, 2, 3. Oh, right, I have to stop it. 1, 2, 3, 1, 2, 3. So you can see, like, right, it's a wait, why is it more? This is weird because it's because it's UD. Oh, it has some blacks. Okay, so you can see this is UDP connection being established. Now if we're trying to go into the folder that's XDP, make it, then let's run it. It's, XDP. Once again, do remember sudo. So now we have BPF program attached. It seems like nothing happened, but when I'm trying to send the UDP connection, nothing happens, right? So that's how it's set. That's how it's set up firewall group. But you can see it works vice versa because we're blocking. Remember, we're blocking the connection established on the port 1111 for the local host. So it's gonna be one way of communication. So let's have it detached, right? Then let's send it, and you can see that everything got resumed. So that's XDP use case. It's quite, I think it's easier. It's a lot of companies actually use it. It was a replacement for IP table, as we were going to see in the paper. So it's, yeah, I think it's most natural use case of the packet filter. It's being an extension to the Linux to solve the problem of the Linux networking stack. Okay. So the last example we can have is the BPF in security, which I have to say I'm not a master of. So there are a lot of things to manage, like security models, for example, file accesses. It's just a bunch of hook in strategic location critical for security. For example, can you do file open, permission, mmap, blah blah blah. And those are the kind of things can be managed by user specific security hooks. All the hooks are there in the security.c. You can check out bootlink for where the hook points, and then traditionally implemented with the Linux kernel modules. Of course, it was extension, but now it's BPF programs are sort of like replacing it. This example is very complicated. It's a little hard to use. So I think probably we won't run it. I have a README file. It's how to run it, how to set up a user that's sort of like and mark it as compromised. Then we will like check, like use the BPF map. Let's see the code actually. So this map is to keep track of if the user is compromised. If the user is compromised, it's the value of it is bool being like true. So the key is the user ID, which is the 64 bytes, 64 bytes user ID. And then if it's compromised, then what are the hook points? Then do not allow if the user is compromised, then don't allow it to open any kind of file. And doesn't have file permission, blah blah blah. It just doesn't allow it to open anything. This demo is really it's killing me. It didn't work on my first pass. But I do have a README file here, so it just lets you get your own UID or it lets you simulate a UID. You run it. Should we try? Do you want to try it? I guess we can try it. Okay, that's it's also helpful for the Linux command tool, which allow you to use BPF tool, which can show all the map that's loaded. So let's go into 4. Finally, last example. So we once again also execute this. Now we can see that let's try to do. Let's see all the maps, okay? So this is the BPF map. So the map ID, every map has an ID, right? It's 4, so the map ID is 4. The hash means the hash map. Name is compromised use, right? Flags. I don't know what is flags, but key is 8 bytes, value is 1 byte, which is the total. Max entry is 100. Memlog, I don't care. MTF ID. BTF ID. It's BTF. It's an advanced topic. Just I have a slice for it, but you can try to Google it for yourself because I never used it myself as well. So what we want to do is that we want to add a compromised user because we don't have the complicated logic. Usually we have some like it's a lot of the security projects are like having ML machine learning models built into it to like detect what users are potentially compromised. There are a lot of projects fit. I have some pointers by the end of the slides. So that's a lot of the use case. So the detection of the user actually is not implemented in the BPF. But the ML model is not in the BPF, obviously. It's just but it helps you with how to control the access of the user. Sort of makes sense. We can try this, like for example, didn't run on before class, so I was a little worried. So the ID is 4. The key is how do we convert this key? It's a UID right now. How do we get the user ID? There's like ID got U 20015. How do we convert it to that's a little complicated. How do we convert it? I think A5. It's decimal tracks, yeah. 4E to F, right? What's wrong with the value here? What's this error parsing byte? Do you mean I think this is wrong with the ID. I think my documents was a little wrong. Anyway, that's how this is a user interface provided by the BPF tool, which is a command line tool in the Linux that help you interact with this. Well, okay, I'm sorry it didn't get to run this, but let me try after class. But this is how you basically you can update the map because the user logic is not here. You can see this access control. That's a very thin layer of it's no logic in it, just program attach and detach. So that's one of there are tons of great projects for the security use case. Falcon, Tracy are two things that I think I consulted with Yannis, and he said those are pretty good because I'm not big into security, so you might have to look into this yourself. It's usually combined with the auditing or detection tool, which yeah, if you want to be trendy, ML probably. So the only project I've seen is it's using like some clustering algorithm to detect user and use it with eBPF. So there are advanced topics. Those are mostly pointers. I don't know any of them actually. I never use any of them actually. But yeah, so skeleton is okay. Like so compile one, run anywhere. It's a simple idea to let you to be easily port data structure. So if the v1 runs in so that means a kernel with the v1 definition is okay to a code that's assume the kernel definition is v1 can also run in v2, although it doesn't work vice versa. So you can see it as being back compatible. And I don't actually know the internal of it. Might need to Google it.
I don't think we should concern ourselves with here, right? Because you're all going to be trying to Debian distribution, it's going to be static.
Yeah, it's not. Is if you're yeah.
So this is a question about you. You're talking about doing like ML inference or something. Would that require writing like the inference code in eBPF?
No. The ML is all user code.
You user space.
You determine which user is invalid and you control its access with the BPF. Right.
So then the user space variable would signal to BPF somehow when it like I can
Yes,
see that
it
one direction.
interacts it with the map.
Because can user space program alter the map?
Yes, I can update the map like we see like for example the syscount example, it clears the map every 5 seconds, right?
Oh,
So look for yourself, I guess. Cool project. Okay, that's I don't know why this is here actually. VCC BPF trace for yourself. I like scheduling, so I post scheduling SCHED here. I was trying to run some example. It's gonna be really chaotic, so be prepared if you want to try that. Other good tools for learning, I guess. This is a most pointer. It has literally everything. It has all the things that you could be interested in. Search on GitHub, search on Google, try asking people. This is a peek into the BPF verifier if you're interested in verifying. It's a 200 slides from really sophisticated engineer. If you're interested in how what's the internal of the verifier, because it's very hard.
Yeah, my suggestion is
Don't touch it.
another rabbit hole.
No, that
Because it's not gonna help selecting your project.
yes.
Right, it's maybe at some point Google search when you
Yes. Google is your friend. ChatGPT is
you
your
get stuck with something verified.
Yeah.
Reject it, and quickly checking the validation, but understanding the verifier is way beyond.
If you're feeling daunted by this lecture, check out this video. It will make you feel so much better. This person is aiming at making eBPF accessible to everyone. So he developed they have an organization called IO Valent. So, but basically what it does is try to make eBPF as accessible as possible. So a lot of great use cases, really, really easy to use tools. So if you're feeling daunted, check out this one. It will help you boost your confidence. Lastly, I would strongly recommend everyone to read this guy's blog. He is a staff engineer, like principal engineer at Intel, previously at Netflix. He is the author of the 2 books, System Performance. If you've seen this flame graph, is actually his implementation is the most popular one. And he has this tool, the BPF performance tool, which also introduced some BPF internals. I borrowed some of the material from his presentation. It's BPF internals, 122 pages. This is how it is. That's all of BPF. I don't want to show this to you because it's gonna scare people away, but it's actually not that easy. Not that simple. No, not that hard after. Hopefully it's not that hard after this lecture. So that's all I've prepared, and thank you for bearing with
A
me.
couple of questions.
Yeah, please
Very
throw me with
interesting.
questions.
Thank you. And
Thank you.
do you have any questions so far?
Like throughout the just if you have questions, just pin me on Slack. I'll
Two things, we need the slides posted, right?
yes,
So-
it's definitely gonna post it right after class
And the way we post this
through Slack.
to Slack, and we're just gonna give a link,
Just the link, I guess. Yeah.
so there's somewhere in the document.
Yeah.
Everybody should have access to.
Mhm.
Yes.
Yeah, of course. I'll do both.
And the programs that are basically being expected today, they also go to cover the previous.
Yeah,
videos, so we're modifying it. so-
Yeah, I will post it. I will try to clean it up and post it by tonight. So the links, I'll have everything. So it's just by today. So
2 minutes left here.
yes, we have.
Safety, right?
Yeah.
Take it deep from there. So a couple of things, let me just.
Okay.
Update on my puzzle, because last week we had to figure out how many people are registered. Who does what?